So today's lesson is probability. So we're going to talk about probability theory. We all have a sense in which our lives are not determined. So if I go outside, it might be sunny, it might be raining, it might be cloudy, maybe it's like raining rocks. That's a very rare event, but that's a possibility. It might be hailing. So many different things can be happening, right? So that's one example. If you're thinking about the stock market, it may crash, it may go up, whatever stock you're interested in. It may go down like $4. It may do many different types of things. In your life, you might have a girl, you might have a boy. If you're having kids, if you're playing cards, if you pick one at random, you might get number one, you might get number two, you might get number three, many different possibilities, okay? So we have the sense in which many things could happen. We can get into a philosophical discussion thinking like, is this determinism or is this apparent randomness real or is it just imaginary? Okay, so I'm just going to go into a little bit of a tangent and talk about this issue. Okay, so the reason why something could be random, appear to us random, but is in fact deterministic or not really random is through this phenomena called chaos. Right? So chaos is where you have a deterministic system. You can write down the equations. I'm going to write down like an example of an equation, of a differential equation. You don't have to follow this part. I just want to get you comfortable with what a differential equation would look like, right? So this is a function. It's a vector. A vector means it's many different numbers stacked together. So it could be like x1, x2, x3, and so on, to xn, however many dimensions you have, right? If the vector is a position of a particle in the board, then the vector is two-dimensional. This is the origin. Here's your point, and here's your vector, right? The equation would tell me, okay, I'm starting here. Where is the particle gonna go over time, right? I have a parameter, call it time. And then you want to give me an equation, dx over dt equals f. I'll tell you what this is in a second. You don't really have to follow this part, but I want to get you comfortable with looking at this equation. Right? It's a function of x and t. What does that mean? It means, okay, x is at, let's say, time t equals 0, x is here. We start here. F just tells you where is it going to be a very small amount of time later. So let's say you wait for a very, very short period of time, like delta t, like let's say 1 microsecond. Right? So this is a very short period of time. So this differential equation becomes, it just tells you that x is going to move a certain amount. It's going to move, let's blow it up. Let's zoom in here. X is going to move from here to here. It's going to be a vector. This is delta x. And that's going to be equal to this f times the amount of time that you waited, right? So if the time is small enough, this is equivalent to that differential equation. So f is just telling you the speed, the velocity at this moment, right? It's just telling you where is my particle going. So I tell you where it starts, and you just have to, and f tells me where it's gonna go. This x, many numbers, could describe the weather, right? This could be the position, the density of air here. This could be the density of the air right next to it. This could be the velocity of the air over here. This could be the temperature of the air over here. So you can have many different variables, right, to describe everything. And they interact in some way, right? So this is like the state space. This, if you know all these numbers at this moment, you know exactly what the weather looks like, right? You know the state of the weather at this moment. The problem is, you have two problems. You can't really know all these numbers with perfect accuracy. It's impossible to measure something with perfect accuracy, right? Even this law is not going to be valid for perfect accuracy because our laws are usually approximate. So you don't know something with perfect accuracy. All right? So that's one problem. The other problem is, can you solve this equation exactly? Usually this is a very complicated equation describing like the whole interaction of the entire weather system. So you're not going to know exactly what your initial state is, you're not going to know exactly how to solve this equation and how to evolve it, because if you're solving this on a computer, you're dividing your time into many small steps, and then each time you add this vector to your state, you jump one amount of this, but there's a small numerical error because a computer has to approximate, it has to cut off, like a computer can't have a number with infinite many digits, so a computer has to approximate. So you get an error from there, an error from your measurement, and then you end up with, you have no idea of what's going to happen. So I'm going to go outside, it might be raining, it might be snowing, it might be hailing, it might be anything. You can predict it to some degree, but you can't really know for sure because of these kinds of uncertainties. Alright, so now we can move on to the main point, which is probability theory. Okay, so as we said, in probability, you're doing something. We're going to call that like a measurement. A measurement could be anything. Could be you like picking a card at random, picking like an M&M at random and seeing like what color it has. It could be you going outside and seeing, is the weather hot or cold. It could be that you're looking at the stock price, is it up or down, or by how much. So that's the measurement, where the thing that gives you an outcome. So you have a measurement and then you have an outcome. And the key point that you deal with, or the key thing that you deal with in probability, is the set of possible outcomes, the fundamental outcomes, like the most basic outcomes. I'll explain what that means in a second. But it's a set, right? It could be like rain, snow, and so on. It could be like 1, 2, 3 if you're like picking cards, like 1 of spades, 2 of spades, and so on. There's like 52 of those. So this is your set of possible outcomes. Usually they call it omega, with this symbol, omega. You can call it anything, but it's just the basic, whatever situation you're interested in, it's kind of the basic units or the basic entities that you're going to get back from your measurement. Now, on top of measurements, on top of these, we're interested in another thing. We're interested in something called events. So what is an event? The way to think about an event is through this example. You want to say, what is the probability that the stock is going to go up by $4? Okay? Well, this outcome, the fact that it went up by an amount bigger, like $4 or bigger, is not a single outcome, right? Because, you know, what could it do? It could go up by $1, go up by $1.5 or $2, or go down by $2, or so there's many outcomes, right? There are multiple outcomes, like let's say there are multiple outcomes like 4, 5, 6, 7. All of these correspond to this event, right? So an event is a bunch of outcomes. So I might say, I want to pick a card at random. What is the probability that this card is an ace, right? It could be, ace is just one, could be ace of spades, ace of hearts, and so on, right? So what you have here is a bunch of events, a bunch of outcomes that all belong to a single event, which is you got an ace. Alright, so let's review quickly what this means. Okay, so we have a measurement, and then that gives me a set of possible outcomes like this, whatever they are. And an event, if you look at what are the all possible events, an event is a subset of omega. It's like this event could correspond to all the aces, it could correspond to all the spades, it could correspond to all the fours. So it's a bunch of, so it's a subset of omega. The outcomes themselves, the individual ones, these are also subsets of omega. right? They're special subsets of omega. And I'm going to have another aside here. The set, this is a tongue twister, the set of all possible subsets of omega. Let's do an example. So I have 1, 2, 3, right? What is the set of all possible subsets? That includes the set of all possible events. Well, it could be 1, like this set, could be 2, could be 3, and then you have to say it could be 1 and 2, could be 1 and 3, okay? And as a problem for you, try to continue this set, okay? There should be 8 of them, okay? There should be 8 different possible subsets of this set. So the set of all possible events, or all possible subsets, is this. There's 8 of them. You can write it out. This is usually called the power set of omega, and it's written like this, right? So if this is omega over here, 2 to the omega is this. The reason why it's written like this in a funny way is because 2 to the omega, like if I want to know a subset, let's say I want to know this one, I want to determine it. All I have to do is go here and treat these as like computer bits. If it's 1, then this set is included. So this subset is just corresponds to yes, this one is included, no, 2 is not included, no, 3 is not included. So I have this number. If I want to look at this set, I have 1, 2, and 3. And 1 is included, so this is like this, but 3 is not included. So you have 1, 1, 1. So the set of all possibilities, if you want to count how many different events you might get, you're going to get 2 to the number of elements in this subset. So this is 2 to the 3, you're going to get 8. That's why you're going to get 8 elements here. Right, I hope this made sense. This is an aside. If you are not following, you can ask below. But basically this functions just as a binary code for each set, for each subset. The binary code tells me if the element really belongs to the set or not. And because if I want to write a binary number, there's 2 possibilities here, times 2 times 2. So what you get is 2 times 2 times 2, and that's 8. Alright, so now we can end this by talking about probability. So a probability, again, we go back to here. We have like our set, whatever it is. And probability theory gives me a number to every outcome, right? So the probability of 1, whatever that is, the probability of 2, and so on. Okay? These numbers have to be positive, because what is a probability? The way you imagine, like what it really means, or intuitively means, is that I want to repeat this measurement many times, like 1,000,000 times, or even like 1,000 times, or even 1,000,000 times. What you get from repeating all those times is what fraction are going to be 1, right? So a fraction is the number of ones that you got. So I do an experiment, I got 1. I do another experiment, I get 1. So I got like 1 5 times or 6 times. That's what you write here. And you got that 6 times out of how many trials? 100. So you're gonna get whatever out of n total. This number corresponds to that. So it has to be positive. And on top of that, if I add up all these numbers for 2 and for 3, and you add up all your different outcomes, well, these guys are going to add up to the total number of experiments that you did, right? You can't have more outcomes than the experiments that you did. So it's going to be equal to n total over n total, and that's equal to 1. That's why the probabilities have to add up to 1. So that's all. A probability has to, you assign number to every individual outcome, and then they all have to add up to 1. And if I tell you what is the probability of an event, like I get 1, 2, and 3, what is the probability that I get a number that is smaller than 3 or equal to 3? Well, that's just P of 1, plus P of 2 plus P of 3. This number, like, we can write it as probability. Let me just put this here. 1 or 2 or 3. I hope you can read that. This is 1 or 3 or 1 or 2 or 3. You just add them up, and this is gonna be necessarily a number that's smaller than 1. It's between 0 and 1. So that's an example of how you calculate for an event. One last thing I'm gonna say. Let's say here, how many possibilities do I have? Let's say I have 52 possibilities. Okay, if I have 52 possibilities, and let's by assumption, assume that each one of the outcomes have the same probability, right? So if I'm picking a card at random, so let's say the cards are well shuffled and everything. When you pick a card, we have no reason to say that an ace is more likely than number 3, right? So every card is the same as far as we can tell. Same thing when you flip a coin. Everything, heads, why would it be heads and not tails unless somebody is cheating or the coin is not really symmetric or something like that. A lot of the times we get a number of outcomes and no outcome is more special than the other, right? So each one has to have the same probability. You have no option, right? So in that case, because of the symmetry between the outcomes, in that case, each one has the same number and you have to add them all up. P, this is P plus P plus P, and you have to add that 52 times, so you're gonna get 52 times P equals 1 because of this rule. So what you get is the probability has to be 1 over the number of elements in omega. If your elements are the cards, then it's 52. If it's, or 53, I don't remember. Or if it's something else, like if it's rain, if it's rain, snow, and things like that, and you're just dropping in, if you're picking like a day at random out of the calendar, and you don't know, it's equally likely that it's raining or snowing or something like that, then you also have like 1 over 3, like for snow, rain, and shine. That's for the sake of example. In reality, like the weather is not going to be equally symmetrical. Maybe it's more likely to rain than snow, but for the sake of argument, we get the idea.